especially to Nijamuddin Ali, Assistant Professor of Mathematics. My subject is economics, and I have already completed my PhD in the Department of Mathematics in Nigeria and applied basic trigonometrics in economics under Dr. Shamuddin Kaur. I saw the subject of mathematics is only the subject which has no boundary of applications or entry or exit like wind. Therefore, I must say, without mathematics, there is nothing you can do. Everything around you is mathematics. Everything around you is numbers. With this, lastly, I conclude my speech. Again, I should express my sincere gratitude to our eminent mathematician, Professor Chandra and Professor Shotajit Roy, and wish the winner of the mathematics department will be grand successful. Thank you, and over to Dr. Nijamuddin Ali. Okay.
Sir, your video is mute, please.
Thank you, Professor Devnath. Thank you for your valuable speech. Now we handed over our microphone to our respected principal sir to say something about the webinar. Principal sir.
Yes, sir.
Principal sir. Are you here? Okay.
প্রিন্সিপাল স্যার আসেননি না?
প্রিন্সিপাল এসেছেন কিন্তু উনি সামহাও কমিউনিকেট করতে পারছেন না। প্রিন্সিপাল আছেন আমি দেখতে পাচ্ছি আছেন। উনি সামহাও কমিউনিকেট প্রবলেম উনার ভয়েসটা মিউট করা আছে। উনার ভয়েসটা মিউট করা আছে।
Okay, sir. He is connecting to audio. Sir, audio is not coming properly. Principal sir, check again the audio.
सर प्रिंसिपल साहब को प्लीज फोन कर दो तो उनको सुनाई दे जाएगा, सुनाई नहीं दे रहा शायद उनको।
Okay, okay.
আর ভয়েস মিউট করা আছে।
Hello.
Yes,
it's
sir.
okay.
Yes, sir.
Okay,
You
carry
are
on.
audible.
Okay.
Okay.
Okay. Thank you. Honorable distinguished speakers, Dr. Bhavani Shankar Dandapat, retired professor, Physics and Applied Mathematics Unit, Indian Statistical Institute, Kolkata, and Professor Satyajit Rai, Department of Mathematics, IIT Madras. My warm welcome to both of you on behalf of me and the faculty members of our college to spend your valuable time for this webinar. I convey my appreciation and congratulations to both of you for giving your consent and feel proud to meet you through this webinar. I also welcome all of you participants in this webinar. All educational institutions have been shut since mid-March due to COVID-19 pandemic. This pandemic has affected education system worldwide, and approximately 25 crores learners in India and 1.725 billion learners across the world are currently affected due to this pandemic. Actually, this pandemic has shocked the whole world and learned us to adopt new ideas in the field of education. I am happy to convey that our mathematics department and IQAC jointly in this pandemic situation of COVID-19 has arranged this international webinar on recent advances in mathematics. And I appreciate their sincere efforts for it. Mathematics is very useful in everyday life. Math can help us do many things that are important in our everyday lives. Here are some daily tasks for which math is important. Managing money, balancing the checkbook, shopping for the best price, preparing food, figuring out distance, times, and cost of travel, understanding loans, understanding sport, playing music, baking, home decorating and remodeling, sewing, gardening, and landscaping. In everyday life, math is very important to us. Geometry and trigonometry may help your child who want to improve their skill in sports. It can help them find the best way to hit a ball, make a basket, or run around the track. Algebra will help them with money to calculate interest and compound interest, and they can use this skill to manage their money now and when they grow up. Actually, mathematics is a methodological application of matter. Mathematics makes our life orderly and prevents chaos. Certain qualities that are nurtured by mathematics are power of reasoning, creativity, critical thinking, problem solving ability, and even effective communication skills. I ensure that from this webinar, all of you be enlightened and hope its success. Thank you very much. And I request Nizamuddin to continue the program.
Thank you, our respected principal, for his valuable speech, which indicates how mathematics is important to our life. So we forward our next speech. I invite Professor Osim Mukhopadhyay, our senior most faculty member, to say something about our webinar.
Good morning.
Good morning, sir.
Distinguished principal. Good morning. Distinguished principal, our guest speakers, Professor Roy and Professor Dandapat, teachers, colleagues, and my fellow participants. Heartfelt welcome to you in our webinar, Recent Advances in Mathematics. Vivekananda Mahavidyalaya Mathematics Department has organized this webinar mainly based on fluid mechanics. Two speakers are renowned speakers. I will say something about them. I am sure you are all have been eagerly waiting for this day to visit this webinar. Our mathematics department are very rich in subjects, faculties. It is audible?
Yes, yes.
No problem, sir. Everything is fine. Please continue.
Okay. I would like to say something about the speakers. Our first speaker, Professor Satyajit Roy, he awarded his PhD in 1993 from IISc Bangalore and joined as assistant professor in BIT Mesra in 1994. Presently, he is working as a professor at IIT Madras since 2006. His research interests are convective heat and mass transfer, and computational fluid dynamics. 8 PhD students already awarded PhD under his guidance. He was almost examiner of more than 100 PhD theses, published more than 130 papers, and reviewed huge number of papers in different national and international journals. And he delivered his lectures in several seminars and webinars in international and national level. In 2018, he elected as a fellow of National Science Academy. He will talk on the topic, perhaps linearization of differential equations. That's it. Next, our next speaker is Professor Bhavani Shankar Dandapat. He awarded PhD in 1978 from IIT Kharagpur under the guidance of renowned Professor A.S. Gupta, and subsequently joined as a
Sir, microphone mute है.
Sir, your microphone is mute, sir. Asim, sir, microphone is mute. Please open.
Osim sir, please unmute your microphone. Okay, sir. Okay, continue. Please continue, sir.
Okay. IISc Kolkata, and he became professor in 1990, head in 2006. He also worked as as dean and subsequently director of Sikkim Manipal University. Thereafter, now he is retired professor of ISI published almost 90 research papers. He is PhD student. I am one of them. He is my teacher also. I am lucky enough for getting his guidance, and still now associated with at least 7 international journals as an associate editor. And that's enough. Professor Roy, are you present here? Professor Roy? Oh no, we'll join at 11:30. So I have to wait.
Okay, sir. Okay. Sir, continue. Sir, please continue.
So for the research topic of lecture topic of Professor Dandapat is onset of thermal convection, a gateway of hydrodynamic stability. This is very nice and interesting topic in hydrodynamics. You will enrich enough with this topic. And the topic of Professor Rai is linearization of. I do not find it somehow. Linearization techniques of boundary value problems of differential equations. So, next speaker, Nizam.
Okay, sir.
Next speaker.
Thank you, Professor Asim Mukhopadhyay, to introduce our valuable resource person, Professor Dandapat and Professor Roy. Now I invite our head of the department, Professor Anandamoy Mukhopadhyay, to say few words about our seminar. Please, HOD sir.
उन्होंने अपना माइक्रोफोन म्यूट कर रखा है।
Professor Anandamoy Mukhopadhyay, are you here? Professor Anandamoy Mukhopadhyay, are you here?
सर कॉल कर दो सर, आप उनको कॉल कर दो अपने मोबाइल से।
Okay, sir. Okay.
Okay, Nizam, I will call him.
Professor Mukhopadhyay, he is not available.
Phone karo,
Okay.
phone.
Okay, now we going to pass and come to our respected resource person, Professor Satyajit Roy. Professor Roy, are you here? Sir Roy. Professor Roy, are you here?
বাবু ওটা অন করা না থাকলে হবে না, ওটা চালাবো যখন দরকার হবে খুলে দিই।
তোমার লিস্টে নির্বাচন আছে।
100 পার্টিসিপেন্টের বেশি হয়ে গেছে বলছে, জয়েন করা যাচ্ছে না বলছে সত্যজিৎ। নিজাম,
I check, sir. I check the system.
হ্যাঁ
Say, sir. Please say till there is free.
I call him.
Okay.
Please arrange his joining.
হ্যালো,
হ্যাঁ
বলছি জুমে বোধহয় ম্যাক্সিমাম পার্টিসিপেন্ট রিচ করে গেছে, তাই উনি ঢুকতে পারছেন না।
হ্যাঁ হ্যাঁ সেটা তো বলছে।
আমি বেরিয়ে যাচ্ছি, আমার
আচ্ছা।
জায়গায় ঢুকে যেতে পারবো।
আচ্ছা আচ্ছা,
আমি ইউটিউব দিয়ে ঢুকছি।
এই হ্যালো বিশ্বজিৎ,
হ্যাঁ বল।
বিশ্বজিৎ, আমি বেরোচ্ছি, আমি বেরোচ্ছি।
Now he can enter probably because
Now it has came.
হ্যাঁ হ্যাঁ ওকে হয়ে গেছে স্যার।
Now you can listen, huh?
হ্যাঁ ওকে
Yeah,
ওকে,
something little problem was there.
নো প্রবলেম।
Thank you, sir. Thank you.
Okay.
ক্যারি অন প্লিজ।
Carry on, sir.
Yeah, you can start now.
Professor Satyajit, good morning.
Good morning. So you start 1 minute. I'll open and keep
Good morning, sir.
Good morning. Good morning. Just I'll open the file and then.
Okay, sir.
This file and then. Oh, this is always little problem. Come back here again, back. See, you can see that. Yeah, now you can.
Sir, start your speech, sir.
His mic is not unmute. Asim Mukherjee.
Sir, share your screen, sir.
You start please.
Okay. So now I'll start.
Yeah, start.
Okay. Okay, then I have to share the screen. Let me see. No, you have to give the option for sharing me screen.
Okay, sir.
You have to give the
Check now.
option.
Okay, sir.
Yeah. Now it is okay, huh?
Okay.
Okay. Yeah. So now you can see the screen.
Yes, sir. It is visible, sir.
Good.
Carry on, sir.
So anyway, I am just now ready.
So this thanks, Dr. Asim. I think he might have talked about me, this, that. I was not here. So anyway, it is okay. So now, good morning to everybody. What is my plan of talk today is some linearization technique for nonlinear differential equation. We'll cover for ordinary differential equation, single, then system of ODEs, and then PD, system of PD, all those varieties. Okay. So everywhere you face nonlinear differential equation. So I have used for, in my research, those nonlinear equation we have replaced by a sequence of linear equation, not one linear equation. So for one nonlinear equation, you will get sequence of linear equation. You are able to listen now, everybody?
Yeah, okay, no problem. Carry on, please.
Okay, okay. So now this technique is very simple. One can learn in a day also, but there are slowly things are there. I'll try to explain the things. So first aim is how to linearize a nonlinear differential equation. Okay, you cannot just linearize one nonlinear to one linear, then it will be too much approximation. So we do a replace a nonlinear differential equation by a sequence of linear equation. Linear equation will be modifying each iteration. And application is very basic mathematics, nothing big is there. Even I have written some pain also, some part, so that one can understand. So this method can be viewed as a generalization of Newton-Raphson. So it is one of the Newton-Raphson type for functional equation. Okay. And we are going to tackle 2-point boundary value problem. So there is one wall and other end is there. So there is two boundaries. Okay, two boundaries is there. We will combine after that linear equation with finite difference and all. So first I have to replace the nonlinear equation by a sequence of linear equation. So it is written again what I was talking. At first the nonlinear differential equation replaced by an iterative sequence of linear differential. This is very important. You have to note it down. We are just not replacing one equation to one linear equation. We are replacing by a sequence of linear differential equation. So one nonlinear equation will give you a sequence of linear differential equation. And some references there, you can go through the theory all developed for ODEs and all. So there it shows that it is generate a monotone sequence of solution, and those sequence is bounded. So monotone sequence one, it is bounded, the iterative sequence converges. So there is no problem if you use this one. So that is theory is developed only for ODE, but we apply for ODE and PD. How we apply, let us see. For PD, theory is not yet developed. Many papers are there, but not that fully things are there. Even we are using the techniques, so we don't study for the PD and all. But ODEs and all, everything is settled. There is no problem. We are using ODE, PD both, but I'll show you how. So now this is a equation, ordinary differential equation, but here so many set of equation is there. That is the problem. Yeah, something else is coming away. I am not doing this. Huh? I don't know. This is this line, how it came in the screen. Anyway, okay. So yeah, so now it has gone. So anyway, so this is the set of ODE. Okay. Now there are so many vector form. It is in vector form. System of ODE is written in vector form. So now to understand this, I am going to show you a single equation. How to do for a single equation, then you may be able to understand this system of ODEs. So for single equation, I have to go a little ahead, and then I have written my handwriting that you have to see. Very simple calculation is there, one page. So I will go a little ahead and show you that calculation. So again, we'll come back to the original page. So this is the basic thing. So some simple case. Okay, I'll increase the size so that you can see. Okay, this is the simple case. I think little I can reduce. This is enough, I think. So now you consider one equation. X is independent variable, and this is a second order equation I have taken. If you have more than second order ODE, then you have to make it a system. Okay, the way you do for everything. So suppose I have a general second order, it will be nonlinear only. So this function phi is a nonlinear function of y dash and all. And there are two boundary, y at a is given alpha, y at b is given beta. Now for a fixed x, I assume that for a fixed x, you have to find out for all x from a to b. For a fixed x, let yn and yn plus 1 are the nth and n plus 1 the iterative values of y. So these are the iterative values of y. I am doing any iteration method in that. Iterative values of y is this, yn and yn plus 1 for a fixed x. X can be x1, x2, anything, any number. So same thing you can repeat for every x. So that is the idea. So now use Taylor series expansion. Okay, so I am trying to expand the n plus 1th iterative stage in terms of nth iterative stage. Okay, very simple Taylor series expansion. X is fixed here. Okay, so I don't do expansion in terms of x, I do expansion about the other argument. 1, 2, 3 arguments are there. You see, these 3 arguments will do. So phi x, y n plus 1, y dash n plus 1 notation already I told. N plus 1 iterative stage. And n means it is n. Other people have to mute their mic. So then if I expand by Taylor series, simple Taylor series, then I get this yn, all this. And then this argument I am taking, so I write partial derivative with respect to this, then partial derivative with respect to y dash plus higher order term. Now, if for sufficiently large iteration, if I am continuing with more iteration, sufficiently large iteration, solution almost converge. In that case, your this nth and n plus 1th iteration almost it will approximately satisfy the equation. Equation is phi is equal to 0. So if for sufficiently large iteration values, then your this thing also will satisfy, this thing also automatically satisfy, and both two are very close. So higher order if you neglect, then you are left out with only these 3 terms, 1, 2, 3 terms. Now these 3 terms, you write n plus 1 one side and nth term other side. Now what is the meaning of nth stage? Nth stage means it is known. Nth stage iteration you know, then only you go on for n plus 1 stage. So now n plus 1 stage is unknown and nth stage is known. Okay, so all nth stage you put right side and n plus 1 stage you put left side. Then you will have first term, I am writing in terms of order. First term is dou phi dou y double dash n plus 1. That is this term. This is the first term. Okay, little I lift. So this term is directly here. Y double dash n plus 1. So what is x1n? This is nth stage. x1n is dou phi dou y double dash at nth stage. I have done only Taylor series expansion, nothing extra mathematics. And then what about this term? Now this term comes here this. Okay. This is y double dash n plus 1. Coefficient is dou phi dou y dash n. Okay. So this is x2n. Similarly, x3n this. And right hand side, what it goes, all nth term I put to right hand side. So yn dou phi dou y dash 10, dou phi dou y dash, y double dash 10, dou phi dou y double dash. So these 3 terms is right hand side. Now I am renaming the equation in this way. This is my equation, which is a linear equation at n plus 1 stage. Linear equation at n plus 1 stage if you know the nth stage. This is the condition. If you know the nth stage, then it is a linear equation at n plus 1 stage. Now, how do you know the nth stage? Suppose n is equal to 0. The 0th stage, how do you know? For any stage of iteration, solutions must satisfy. Any solution, you claim it is a solution, must satisfy at least the boundary condition. So both boundary condition, you choose any polynomial the way you want. You can take a linear polynomial also. Between 2 points, you fix a linear polynomial. So your initial guess may be a straight line, and then that is the 0th stage. Then first stage you get this equation. For n is equal to 0, you calculate all this because dou phi dou y double dash, this will be function of in general y dash everything. So you assume any solution. initial stage, 0th stage of iteration, which is known as initial stage, or you can call initial guess. By knowing the solution, you have to coefficient all you have to find out x1, x2, x3, and x4. This full all are in a stage, 0th stage. So any solution if you start with which satisfy the boundary condition, only boundary condition is given. So any solution you start with which satisfy the boundary condition, you will be able to find out the x1, x2, x3, x4. And then you get the first stage. What is the equation? First stage equation is x1 into y double dash, x2 y dash, x3 y, and this is a linear equation. So if you know the 0th stage, then you have a linear equation. Okay. Then first stage you find out solution for that linear boundary value problem. Then you get second stage. So every time the equation will be changing. That means one nonlinear equation I want to solve. For that I am solving sequence of linear equation. And each solution is monotone sequence and they are bounded. This part is proved for OD. In books also it is proved for coordination technique. So when you generate a monotone sequence, bounded sequence, you have a limit point. So that means your solution will converge. Okay. So now what is the problem here? We have to solve a linear boundary value problem. So if any single, I have taken a single ordinary differential equation, it can be any form. Okay. And then I get a linear boundary value problem, which you can solve by finite difference method or whatever it is. For linear boundary value problem, there are many methods, matrix method, finite difference, multiply and solve, or any other method you can solve, collocation, whatever you want. So, but your nonlinear part is replaced by linear. You cannot solve only one equation because n is equal to 0, n is equal to 2, n is equal to 3, 4, at least 5, 6 iteration. After that, the solution will not change, so it converges. That's what it happens. Okay. If solution does not converge, there is a big problem. So that we cannot handle. I am telling whatever problem we have done, it has converged and it will converge many places. Many people told this, you have checked. And this is a standard technique. Now, I take a simple case and then I show you. Yeah, somebody want to ask, he can alone unmute and then ask some question. Okay. So I just told you the technique for one equation and I am going to apply for a simple case. Since it is meant for many students, so I have done separately added, these are all part, so that I can show them how it is working. Suppose this is my equation, example 1. You do not know any technique to solve this equation. Okay. You just think 1 minute and tell me if you know. Because this is highly nonlinear. You see, series function, all this, nothing will work. So you don't know any technique to solve this problem. Correct? So now I use the linearization technique. Linearization technique is this phi is equal to this. And then I replace by linear boundary value problem. Just now I derived the series. So capital X1 is dou phi dou y double dash, which is x here. Then this is minus 3 y square. You see the coefficient having the function x, y, dash, everything. X4 is this. X4 is this. Okay. X4 is this. So I got x1, x2, x3, x4. Now I got the full linear problem. Now with y is equal to 0 at 1 and y is equal to 1, I want to find out solution. So I consider.
Sir, what?
Yeah, anything you want to
Sir,
ask?
what is X4 here?
X4 is this one. You see X4 I have given, no? Then you have to go back and check. You see X4 here. Whatever the nth stage is there, where here. Whatever the nth stage I put right side, that is as X4. This total quantity is X4. Yeah, right hand side is X4.
Okay, sir.
Is equal to not written. Okay, this total quantity is X4. So all nth stage I put right side, so that is only X4. Okay.
Okay, sir.
Okay, so now you go back to these and you calculate this one for particular equation, no? So it is very easy to calculate. Yeah. So now x1 is dou phi dou y double dash, x2 is minus 3y square, x3 is this. So x4 is equal to y double dash into x1. So this is this one, and then here you multiply y dash. So I multiplied y dash. Here I multiply y. So I get this. Now this big expression I don't want to write because already I have equation this is equal to -8. So if I replace this equal to -8, I get simplified form of x4 is this. So my x4 is this. Now here interesting part, you see all the coefficients are x, y, y dash all. So they are all function, but then x4, x1, x2, x3 all are at nth stage. Then the equation is n+1 stage. So first I have to get some solution. And I have this data for any solution should satisfy the boundary condition. You project any solution, that will be solution. First people will verify whether that is satisfying boundary condition. So whether it is any iteration or any solution should satisfy this. So by satisfying this, I consider one solution. Okay. It has gone a little more. Yeah. So now, see, I have satisfying y0, maybe y2 was there or y5, whatever it is. So now I get this solution. Okay, some solution I have taken. No, this is one more extra. Oh, I have not done this for any solution. So now initial guess you can find out, maybe not written here. This is another problem. So initial guess, how do? You find out a straight line. If you want straight line also, you can find out x is equal to 0, y is equal to 1. This is one point. And x is equal to 5, y is equal to 31. Okay. So this is another point. You can find a straight line connecting this point. So that will be y is equal to ax plus b. Okay. Y is equal to ax plus b. And x is equal to 0, y is 1. So this is 1. And then a also you can find out. Maybe this is 6. Okay. If I write 6 plus x plus 1, both satisfying. X is equal to 0, it is 1. X is equal to 5, it is 30. X is equal to 6, 5, 30, 31. So this can be one initial guess, 6x plus 1. So if this is y is equal to 6 plus 1, what is x1? x1 becomes 0. Does not matter. x2 is something, x3 is something, all you can find out. And then you can put it there, linear equation, and then you can solve. So this is linear boundary value problem. So you start with initial guess. First you start with a straight line, then the solution may come, whether it is increasing type, some type will come. Okay, slowly it will go. So first iteration you may get some different set of points which will not satisfy this because this is initial guess. So initial first solution you have to start with boundary condition, and then the second solution you compute from here, this point. Okay, then third solution again you compute from there. Slowly all things will be done. Okay, you got the idea or not? How to generate the linear sequence of equation and how to start. So initial guess, always we are starting with satisfying boundary condition. Now satisfying these 2 points, you will find a unique straight line. But you can find a second degree polynomial, third degree, which will not be non-unique. Does not matter, any one. Okay, so because Newton's-Raphson method always, it depends on the initial guess that you may be knowing little about the convergence of Newton-Raphson method. So one non-linear equation, so whatever is your problem nature from the physical problem, you choose similar type of profile, which may be non-unique, but which satisfy the boundary condition. I am just showing example. You can start with straight line and then you can start and see that how it is going ahead. Correct? This technique we have applied for many set of equation. I will show you slowly everything. First, you have to understand the technique. Technique is very easy to understand. You can take one equation and do. Now, this is one part. So nobody is asking anything. So I assume that people have understood. Any doubt is there, you tell. Otherwise, I am going to show something else again.
Sir, is it any linearization technique for singular differential equation?
That and all we are not talking. Singular differential equation is little different. Okay. Now where is the singularity? That point, if you remove other part, it is not a singular. No. Okay. We are talking equation. See, if one singularity, definitely any technique cannot help that point. So forget that point, other point. So your domain 0 to 5, I am telling, If there is no singular point, then you may go ahead with this. That type of also equation is there, because I show you one equation, this you cannot solve. Forget singularity and all. Okay, x is equal to 0, maybe it is there are some point that you can remove. You can start with x is equal to 1. So to explain the technique, I have taken something. Okay.
Okay. Okay. Okay.
Then you can go ahead and see what it is showing. Okay. Numerical technique, no, nothing wrong. You can go ahead and see that what is showing. So you are talking about singular point. Without
Yes, sir.
point also, there are 1,000 equations which you cannot solve. Okay. If you know the singular point already, then definitely you will take care of that. So rest part you can do ahead. Correct? So next I will show you another way you want to learn the technique. Okay. Now let us see this thing. Okay. See, you have solved many differential equations. Have you created any time differential equation? That is the question now. Now let us create some example. Suppose y is equal to this quadratic function I take. Then y dash is this, y double dash is this. Then I calculate this quantity is this. So this is a differential equation I created now. I created a differential equation whose boundary values at y at 0 is equal to 4. You can calculate and see. So this equation with this boundary condition has, this is a solution. I know one solution. But you see, this is a nonlinear equation. There may be more than one solution. Huh? Correct. At least there will be two solutions. Independent is their second order equation, and there may be many other theory. I am not going into all details. But I am telling, if you want to learn numerical technique, you just see the experiment, wherever the problem is coming. So here I start with an equation. I start with a solution itself. Just y is equal to some quadratic function. I have taken quadratic polynomial. We are talking about all polynomial equation, not many, because any polynomial type equation looking also is not so easy to solve, because this problem you can't solve. You don't know any technique. There is no general technique to solve a nonlinear equation. If I give you this problem, I have created only the problem now itself in front of you. If I give you now, you can't find out solution. Okay, if I don't tell the solution. But this is definitely a solution because it is satisfying this. No, I have only created now. Correct. So now how to go back to that? So you apply numerical technique and see whether you are going back to that. Now for this, what I understand from numerical experience is you create a quadratic things with this boundary condition, you may be converging there. Okay. So these are all nothing guaranteed. Nothing you can give guarantee, but that's all option for doing nonlinear problem. So linearization technique is one option. And as I told you, many people are applying in many areas. So when you do a research, face a nonlinear problem, what do you do? Either you stop there or you do something. So this is one numerical technique which is vastly used in all fields. Okay. And it is based on only Taylor series. So any nonlinear problem, what if people does? They do only Taylor series only. What else you will have? Other approximation based on a similar, some generalization of Taylor series type thing, something series approximation only they have to do. But here it is very nice. Theory is developed for OD, and this is I am showing for singularity. So if you want to learn the technique or you understand differential equation in better way, then you just create your problem and solve and see how it is working. Okay. Because many people ask many type of electrical problem, mechanical problem, and our research scholars, they have supplied our technique and it has worked many times. You cannot give guarantee every year it will work. That is not true for any knowledge. So this works. Whatever we have attempted, it is work. Now you try and see wherever you face. Okay. Or at least for learning purpose, you learn. And if you want to study more differential equation, you create your example and try to see what is the problem. Now this equation will have more than one solution, but you have created that equation with one solution. So where is the other solution? So there are 1,000 questions you can itself create and solve and study and understand the things. Okay. So what I taught.
Sir.
Yes, go ahead.
Sir, I have a question. I have a question regarding that. Can we find two perpendicular lines from this nonlinear differential equation while converting it into linear differential equation?
Two vertical perpendicular lines means what? What do you mean by two perpendicular lines? Two perpendicular line, anybody can.
Hello, sir.
Those lines.
Am I audible, sir?
Solution of that. What is the connection between the different?
Am I audible?
Yeah, you are audible. You have told two perpendicular line and one differential equation. Now you tell what is the connection between those two lines and the differential equation. You tell. Then only you can find. First you have to tell the
No,
question
sir.
in your mind.
I am asking while converting the differential equation to linear differential equation. So from that we can find perpendicular lines or not. That
You
I
are
am asking.
converting one differential equation to a sequence of linear equation. Where is the lines come in picture? What is there in your mind that you are not telling clearly? What is the role of that lines? Yeah. What is the role of the lines? Lines are coordinate axis, but a coordinate axis here nothing is there. Differential equation only one x independent variable. Y depend on x. What is the line playing role? You are thinking something which you are not able to express maybe. Understood? We are converting a single equation. Our aim is to solve that equation. So we are converting by a sequence of linear equation. We know how to solve linear equation. We are solving. Now you are telling while converting perpendicular lines, what is the connection? What you are thinking in the mind? Can you tell clearly?
He is seeking, perhaps he is seeking a solution.
Which way?
I don't know. I don't know. I just guess it.
Yeah, that's what. Maybe he's
Hello.
always there will be two perpendicular lines is a solution of that. Where is that?
Yeah.
These are all nonlinear curve solution will be there. Line, oh, I have taken one line because I know only boundary point 2 point. So I have taken a unique line to start the initial guess. That need not be line. You can start with quadratic also, but it will not be unique.
Please, participant are
You
requested
understand?
to
Anyway,
put
you
their
get
question in chat box.
some idea about lines or something. Then you can ask later also. But you have to first is what is the important point here? You have to learn how to solve one linear equation. That is we have taught that how to convert it, and you can read those reference also will give. You can read and do. And I have shown you another handwriting that how to create equation and go back there. Whether you are able to go back. You will not be able to go back. I am itself telling how to go, why you are not able to go back, what is that thing. But if you substitute, it will satisfy. You may be able to go back, you may not be. We have not gone and test all those things. But I am telling you how to study. So I am giving you 1,000 questions. Okay. But you learn this technique and then understand. Correct. Because you have to apply this technique in some research.
Not appropriate.
So I think you understood the technique. Okay. After that, you are having question. You are having question.
Okay. Participants are requested to put their question in chat box.
Yeah. No, they can ask also. They can ask also. No problem. Let them ask because otherwise they forget.
Continue, sir.
Yeah, because the material is little less. We will stop in time. Don't worry. We will not. At least let them learn little. Whatever they are getting, let them learn.
Yeah, sir. Yeah. Okay.
Not a problem. Let them ask the question. We'll listen because we are seeing now all those things. So now I have given a simple equation and how to do it, and then create your own example and do it if you want. Okay. Let me see what else is there. I think these are all maybe after that I have some technique for this linear equation also how to solve. So generally after one equation, if you linear, I will mention Thomas algorithm. This is taught in MSc syllabus. Whether all people learn or not, I don't know, but it is taught in MSc syllabus, this page. Okay. So here it is showing the boundary value problem, linear equation. Your AI, BI, CI are x1, x2, x3, DI is x4. So you generate a system of linear equation, and this is the iterative, this is the reconciliation for that system. Okay, tri-diagonal you will get, correct? This is I was doing there. If you replace by second order finite difference scheme, linear equation will convert to this. AI, BI, CI, DI will depend on your this thing, x1, x2, x3 all, correct? So this is linear system of equation, how to solve linear system. linear system you will solve by Thomas algorithm. What algorithm tells that you choose these 3 recurrence relation, you convert it to 2 recurrence relation, and then you derive for I minus 1, then you replace here I minus 1, then you get directly 2, yi and yi plus 1. Now, I satisfy the boundary condition, y1 is equal to alpha. This is your, I was taking y0 is equal to 2 and y5 is equal to 31 something. So you satisfy this, that will give you w1 should be 0 and g1 should be alpha. So once you give that, then this holds for any y2, correct? Now, once you start w1 0, g1 alpha, you can find out wi with this expression. All w2, w3, wn you find out and then come back substitution. So this is only Gauss elimination and back substitution, which is taught in MSc syllabus, how to do a linear system of equations. See, one nonlinear, you get a linear sequence of equation. Now each iterative stage, you will get a linear system of equation, because if you apply the different scheme, you get a tridiagonal matrix Ax is equal to B. You will not be able to invert this matrix, because Ax is equal to B, very easy to solve X is equal to A inverse B. But if this is 100 by 100 matrix, you will not be able to invert. And since there is a big zero, only tridiagonal, these diagonals only non-zero, so you should do elimination, which is known as Gauss elimination, simple Gauss elimination. You do Gauss elimination, then you reach the other boundary, or then from other boundary the solution comes. So first you will get yn plus 1, yn you will get, then yn minus 1 you will get, slowly everything you will get. So for all x, you get a solution. So this is Thomas algorithm. I will be mentioning this, so just I mentioned. These are all little more explanations there in handwritten. Okay, now you come back where we are starting. So I explained for single equation, it is very easy now to understand. So now here it is system of ODEs. This is general theory. You see the Taylor series, same thing we have done here. These are the phi 1, phi 2. Instead of psi here, it is a phi, little different form it is written, that's all. So each Taylor series, each derivative you have to do for vector equation also, correct? And then you get a linear equation, and then you discretize the domain A to B. A and B are the two boundary, okay? And once you discretize with this finite difference scheme, you get this. This is solved by Thomas algorithm. Just now I have shown you Thomas algorithm. Now here, if you take one equation, your capital A and B and C are scalar, but if you take more than one equation, then it will be a matrix. So you will get a matrix in coefficient whose elements are also matrix. Okay, now you see the example. You will understand better in example. Take this equation, this Fognard-Scan equation. This is one nonlinear equation. Everybody knows in fluid mechanics. Now this equation, it is a third order, so I convert it to second order. Okay, second order. Now this problem I am trying to solve with these two boundary. And how to get the small f? Once you get capital F from all this technique, then you integrate every time capital F, each stage you get the small f in the program itself. Okay, this is my phi. You see phi is also there. I explain with phi. X is eta and your capital F is y. Small f is also fixed. Or we are not doing anything linearization with respect to small f, because small f every time we are integrating and finding every stage. So this is a single equation, nonlinear boundary value problem. Now I write linear. Then I calculate x1, x2, x3. Then I put the difference equation. Then I get this one. This one just now I explained last how to do with Thomas algorithm. This is Gauss elimination plus back substitution. So single equation you write as a sequence of linear equation, and then you get that each stage you get a system of tridiagonal system of linear equation that you solve. Each stage you have to solve, each iteration stage. Because for each k, this is for each k you have to solve. K is equal to 1, 2, 3, like that, each iteration. Then you will do 5 iterations, you solve, the ODE is solved. Okay. Now, see, this is our problem, maybe little early, 2004 around this type of problem. Where this is a rotating sphere, one paper we have, you can see. So this paper, final equation is this. So this is a system of ODE. 3 equation, 3 unknown. Capital F, this is again the fluid mechanics here. A small f is steam function, we go for velocity. So we'll convert this third order to second order, we'll write. and small f will every time separately will integrate in the program and find out. Okay, anyway, no problem. 3 condition is there, 1, 2, 3 for f. F is third order 3, g is second order, there is 2, and this is this. So this is the set of nonlinear ODE, set of nonlinear ODE along with their boundary values. Now I convert this to, I linearize this. So I get 3 linear sequence of equation, 1, 2, 3. Instead of n and k, here it is written in I. But boundary condition is fixed for all iteration because any solution has to satisfy. So boundary condition in the program we are not computing, it is given. It has to take that values. Now this is a coupled system. You see this is G equation, but here also G is there. This is theta equation, here also theta. So all mix. You cannot solve separately F, G, theta. You have to get solution at a time. So here the vector comes in picture. So this set of ODEs I can write in a single vector ODE. Okay, each unknown is a vector component. Okay, so how it is written, you see. So x1, x2, x3, all x1, y1, z1, after linearization you get this. Then you write this different scheme. This is only written for f, you can write for g theta. Then finally you get this. Now this is not Thomas algorithm.
Sorry, sir. Screen is not sharing properly. Screen is not sharing properly, sir.
Your screen sharing, it is written. Screen is not sharing properly means fully you are not able to see or half you are seeing. What you are seeing? What about other people?
No, it is okay. Perhaps problem inside.
Oh, problem is some other.
It's okay, sir.
It's online, sir. No problem, sir.
Sometime because of connection you may not get full screen.
No, sir, everything is fine, sir.
Everything fine. You carry on, please.
Okay. So now if I have started with 3 equation, then I got this linear system. Now here one important point is Thomas algorithm I told I have also intentionally written small a, b, c because these were scalar. Now here this is a vector. No, w is a vector. If you want to go ahead and see w is f dash g theta. This is a vector and these are all matrix. This coefficient itself a matrix. So if I write a tridiagonal system, so this is called a block tridiagonal system. So when the equation is 1, you have Thomas algorithm, which I explained. Now when the equation is more than 1, then you have to write in vector. So solution you are searching in terms of vector form, and then the coefficient become matrix. This matrix inside small matrix are there. So each element is a matrix. So this is itself a matrix because 2 to n is running. I can write in terms of matrix. If I write in terms of matrix, it will look like this. No, first is W1 may be known. You just check it. If you see n is equal to 2, if I put W1 is known. See, W1 will be known here. W1 is the boundary condition. Maybe little more ahead it is given. See, W1 is given. W1 is known and Wn plus 1 is known. So your unknown is 2, 2. So here it will come W2 to W2 to Wn it will come, correct? And here it will come W2 means first one will not come, B2 and C2, okay, and then rest all 0 will come. So you see your matrix system when you are writing, this is a recurrence relation I can write in matrix system. Each element is a matrix. So here Thomas algorithm, not the extension of Thomas algorithm is Varga's algorithm, exactly same. There you are dividing instead of that inverse. Varga's algorithm also explained here. So now you see these are the Wn, Dn, all are explained n, bn, cn. Because you have written 3 equations, so 3 by 3. Each coefficient is a 3 by 3. Okay. Now you are seeing the Varga's algorithm. This is the Varga's algorithm, same Gauss elimination and back substitution. So this is the same generalization of Thomas algorithm. If you write in the, see, you have written now, that time you have seen maybe y and wn and wn plus 1. Okay, see, I had written that time yn and yn plus 1. Okay, correct. So this is, then this is e and j and all these are there. So finally, this is giving you the solution. Okay, you have to calculate e and j and for all. So which is g, wn, omega n and something I have given notation. So it is exactly same. Varga's algorithm is nothing but Thomas algorithm. Thomas algorithm for single equation is Gauss elimination and back substitution, which I have shown in the slide. So you can see also in any book will be there. MSc also we used to learn this thing. How to solve a tri-diagonal system. Okay. So now this is Varga's algorithm because it is block tri-diagonal. So now what I have shown you single equation. This is the first example, single equation, how to solve. Here you get a this matrix system. This is a small a n, b n, c n. So these are all scalar, and you use Thomas algorithm in solve. And here it is a system of equation. Then you linearize. This is the quasi-linearization technique. After that, finite difference. After that, if you apply finite difference, you get the block tri-diagonal system. Then you apply Varga's algorithm and solve it. Finally, you get the solution with the boundary condition this also in vector form. Correct? And initial, how to start the computation. The computation is carried out using the initial profile. These satisfy these boundary conditions. These are the boundary conditions. See, first one is if I put eta is equal to 0, this is 1 minus 1, 0. If I put eta is equal to 0 here, then it is 1. Eta is equal to 0, 1, 1. 0, 1, 1 at eta is equal to 0. This is at eta infinity. At eta infinity, you get eta infinity means e to the power minus infinity is 0. So 1, and here it is 0, 0. So these are the boundary conditions satisfying by the. Why I have taken exponential profile, I have not taken linear, because our solution, all boundary layer equation, these are the exponentially it change, asymptotically it reach the boundary condition. So I know well before I know that my nature of solution. So I am searching such type of solution. So that is only little bit important. As I told you, the Newton-Raphson is very sensitive about the initial guess. If I take linear, anytime we get the same solution, but there may be problem also. In between some other solution is there, it may go and converge there. Okay, because it may have more than one solution also. So what is the exponential solution? I am the searching. So because the physical nature of the problem. So if you are working in electrical engineering, this thing field or mechanical engineering, you have some rough idea about the nonlinear system, your expectation of solution, how the boundary varies. So if you have some idea, then it is better. If you don't have any idea, then you have to understand the things. You have to see that, because initial guess, different initial guess may get different solution. That is the property of Newton-Raphson method. Any nonlinear equation, algebraic also, once you find out the root, you might have studied. Okay, you might have studied the root, finding root by Newton-Raphson method. There also you can land up with different root. Okay, if there is very close to roots, then it will fluctuate also. So many things are there. So those are the things you have to face with the nonlinearity. There is no other go. But with the background of your area of research, you can choose a particular profile and then see that. It may be easy sometimes. And we have applied on this technique on many problems. Okay, not one, two, many problems. And this is all about ODE system I have shown you. See, very recently people, our group itself using, see, this is 2019 paper, maybe I'll show you. This is 2019 paper, maybe somewhere it is there, 2019, yeah. Latest one paper I am showing you. This is liquid, oxygen, hydrogen, some fluid mechanics problem. Okay, fluid mechanics problem, what is the final thing is coming? See, this is a set of equation. This is the set of equation, okay. This is a set of equation, very complicated, you can see. And then this is the final, which we are going to apply. So here we are going to apply this. This is a, you see how many equations? 5 equations, 1, 2, 3, 4, 5. Concentration, some heat and two side velocity component, all are there. These are the 5 equations, nonlinear equation, all coupled. You can see, very complicated. And these are the boundary conditions. Okay, these are the boundary conditions. So this is PD. This is PD. But what we do here, PD, we write this phi like that we are writing here. No, we'll write independent variable. No need to write, because we are not doing with this j, eta, you write. And then whatever we write, AF, phi we consider F. Then if j also one more argument, Okay, fji one argument, f eta one argument, like this. How many variety you have, you just add all. Okay, f eta, then this is dot dot y, if any other is there, equal to 0. So this equation I will be writing like this, the first equation. F eta is there, f eta is there, f is there, fj is there, h is also there, you write h and all, and then you apply the same way. So for PD also same way we are applying. How many argument, Taylor series expansion, and then linearization. See, linearization version will be there somewhere. I think I have kept this equation. This equation linearized version looks like this. You see, this looks like this. This is the linearized version. Same x1. These people have given t1, t2. x1 is there. x1, y1, z1, t1. All the same notation. So now this is what? Finally, this is a linear PD, not OD. You see, this is a PD. So whatever argument you have, you write same as linear PD, and then you write the coefficient also is there in appendix. Coefficient also you have to give. See, all the coefficient is given, and these are all the full set of coefficient. So whether it is PD, OD, both the places we are applying all the this technique, linearization technique we are applying. See, now the boundary condition is there. For PD, what will happen? It will be 2 dimension. That's all. It is one more extra dimension will increase. So I have to solve for all eta, x, and also xi. I have to go one more variable is there. Here xi, no, here x is there, eta is there. That's all. Two independent variable is there. So for each x, for each eta, I have to solve. That's all. We have done for 3D also, PD with unsteady problem also, you'll have more than one more independent variable, no problem. That many direction you have to do. For OD in one slot you are getting, yeah, you have to get in that full stretch of downstream you have to get. Because PD is nothing but a sequence of ODs only, one direction all ODs, infinite difference. In numerically, it is not, it is a series of ODs only. Okay, because each step that independent variable you solve as OD. Okay, so this is see, I have shown you just recently also we are applying, and this is we have applied at least more than 50 papers in international. So same technique, ODs we have applied, PDs we have applied for boundary layer flows. Okay, this parabolic equation, it works better maybe because parabolic system is a marching system with respect to time. Hyperbolic and all may not be that much smooth, but in many cases you get solution. Okay. So you have to check whether it is, wherever downstream marching is there, that type of problem, something is progressing with time, so progressing with the coordinates, like fluid flow problems, you may be able to use this technique efficiently. Otherwise also any nonlinear OD, also you can try and see how it works. Even many places people are working like population dynamics, biomathematics and all also. I have seen people are using coordination technique. You just type coordination technique and or Newton's linearization, you will see that how many fields people are using. So in many areas people are using for solving nonlinear boundary value problem. Whether it is OD, single OD, system of OD, single PD, system of PD, people are using. Okay, so that's how I explained everything with the this thing. Handwritten also some more part I have added so that you understood. And to understand that, create your own ODs and try to solve simple cases. Okay, then my part I think I have done. Another some 5 minutes are there or something. Anyway, people have asked in between also question. Anybody who wants to ask any more question? Another 5 minutes.
Session is open for question. Participant can ask question to our resource person.
I can, it is not a question.
Okay,
I can,
hello.
May I tell something?
Yeah, anything.
Oh, actually one people proposed me that this type of equation can be solved by central manifold theorem. Have you any idea? They provide me a book to learn. Actually, is it?
See, any manifold, you go ahead with any manifold to understand the system in a simple way. That is the idea. See, you go in higher dimension to understand but I have taken here everything in Cartesian system, 1, 2, 3 dimensions. So now if you have a complicated problem, you go in higher dimension, higher manifold, you see in a simple way. So there, anywhere it can be applied, because then your Jai will be in that manifold coordinate system. That's all. We are taking a simple
that
X.
is also,
yeah.
that is
Manifold
also
people, see,
iterative
anybody
technique.
go, see, there are things people are studying many manifolds without knowing where it is applicable, but some people are applying also. So when they are applying, they know that in that manifold or in that dimension, their equation is looks simple. So there you apply with that variable. It is Taylor series is applicable in any manifold.
Yeah.
That we are applying only Taylor series. So it
Actually,
is
that is similar to your lecture.
Yeah, people are applying.
That is similar.
Similar.
That is also an iterative method.
Yeah.
Actually, he is provide me, he is an Australian professor, provide me a book and proposed something about.
You have only Taylor series to do something. Nothing else you have.
Thank you. Anyone can ask any question. Audience, from audience, please ask.
Sir, there is one question from Aditya Das. He wants to know about the FD scheme, which you have mentioned.
Yeah, finite difference scheme is just, it is a central difference in the, for OD one direction only. Central difference scheme we are using. And if you are using 2-dimension PDEs and all, we are using one side forward difference and another side central difference, always in the cross central difference. So this is just simple finite difference scheme, what you learn in MSc itself, that's all. So with that time central difference scheme, you can generate a linear system of equation Ax is equal to B. And then if it is a single equation, you can apply Thomas algorithm. That is also included in MSc syllabus. Even it is 20-30 years before when we started it. Okay. But maybe that time we have not learned. When we do research, then we learn properly. But that's the reason I have explained in that handwritten I have given.
Correct, sir.
So that you can understand.
Sir, there is one more question from Sanchita Seth. She wants to know, according to the problem, can we change the exponential function?
Yeah. According to the problem, you have to choose your initial profile because it is based on generalization of Newton-Raphson. If you are doing mathematical biology problem, they are somewhere maybe exponential useful, somewhere maybe quadratic useful. So you can test it. See, nonlinear equation, you may get which solution you are searching, you may not get that first time. You get something else. Then you have to understand where is gone wrong. So because there are many solutions maybe. You may get more than one solution also. There are multiple solutions in nonlinear problem. So all these are there. So numerical technique will not give you guarantee anything. You have to understand the system. You have to verify with the solution. You have to again come back. So this is the case.
Yes, thank you, sir.
Linear equation, if you take, you are through. One slot itself, you get solution. That's all over. Even numerical technique with Thomas or Berger. So these are a lot of interesting things you will face when you start applying this type of technique in research. So that experience. Okay. Now it is only for learning. Okay.
Is there any question from audience? Professor Taman, check our YouTube live and there is any question? One participant, Tapos, are you asking something? Kindly unmute and ask your question.
Is our next speaker attended?
Yes. Professor Dandapati is here.
Okay.
Professor Taman, check our YouTube live.
Yes.
Sir, some participants are follow our YouTube live channel. We are checking is there any question or not. Okay.
Someone asking what is the limitation? What are the limitations of linearization technique?
Limitation means that partial derivative we are doing, all those things should exist. That is generally no problem because many polynomial equations are there non-linear. So limitation is just partial derivative we are doing, no Taylor series. Whatever Taylor series limitation, similar thing. That's all. But generally, stage it never come because before that itself, see if some equation coefficient you have 1 by root y square minus 1 and all sorts of things, like one person was asking, no singularity and all. So those type of things you have to do when you are solving. You have to take care of those. Otherwise, it may not converge. Then itself you will understand where is the problem. Okay.
Professor Thaman, is there any question in our YouTube channel?
There is one question from Bit. Hello, am I audible? No.
Yeah.
You can itself read.
Achha, there is. Yes, sir. There is one question from Bidyut. We have used method of adjoint for solving nonlinear boundary value problem. It is useful when boundary conditions are implicit in nature. I guess explicit boundary condition is also can be handled. So is it possible or not?
Which one? You have done something else method they are telling. This method. Boundary condition, yeah, okay. If you want to know that this method boundary condition are explicit, but you can have differential equation in the boundary condition also. That is not a problem. That you have to numerically look into it. That is not coming picture in with this technique. Generally, numerical, what we do if the differential equation, boundary value problem, boundary condition also is a differential equation, we again put finite difference there and we put the adjust in the program. It will not disturb your technique. Technique is for the equation. So boundary condition can be anything. What is the help I am taking? Boundary condition should allow you to guess the initial solution. That is only the help. So it is nowhere coming picture with the technique. Boundary condition is separate. Okay, it will not.
I think we don't have any more questions, sir, from.
Okay, then I have class 12:40. So those
Okay, sir.
will start.
Thank you. Thank you for your valuable speech, sir.
Okay, thank you. So I will now leave. So I will now leave the meeting. Okay.
Thank you, sir. Thank you so much.
Okay, welcome.
Thank you.
Okay, thank you, Asim.
Thank you, sir.
Yeah, thank you.
Nizam, Professor Dandapat attended?
Yes, sir. Dandapata is here. Now we going to our second speaker. Professor B.S. Dandapat.
You please arrange.
Somir, stop sharing. Professor Somir Tamang.
Hello.
Please stop your screen sharing. Professor Tamang, are you?
Samir, please close your tab. Screen sharing.
Okay, sir.
Okay, thank you, Professor Tamang.
Okay, sir is present.
Now I introduce the responsibility to our second speaker, to our senior most professor, Asim Mukhopadhyay. Kindly say one or two sentences and hand over the mic to our speaker, Professor Dandapat. Professor Mukhopadhyay.
Welcome, sir. I have already told something about Professor Dandapat. Actually, I am repeating again. He is my teacher. And Professor Dandapat awarded PhD in 1978 from IIT Kharagpur under the supervision of famous renowned Professor A.S. Gupta, and subsequently joined as a lecturer as ISI Kolkata and become professor in 1991. And subsequently head from 2006. He also works as a Dean Academics and Director of Sikkim Manipal Institute of Technology. He published a huge number of research papers, almost 90 and more, from different international journals, and guided 5 PhD students. I am one of them. And still now associated with 7 international journals as an associate editor. I am sure his lecture will be very nice. Please, Professor Dandapat, please carry on, sir. Sir, please unmute your.
Sir, unmute your microphone.
Microphone unmute, please, sir. Your microphone is showing mute. Please unmute, sir. Yeah. Sir, carry on, please.
Sir, sound is not coming. Check, sir. Hello.
सर आपकी आवाज नहीं आ रही सर.
Please call over phone. No sound is coming, sir.
Hello.
What is the problem? হ্যাঁ দণ্ডপতির সঙ্গে ফোনে যোগাযোগ করো ফোনে আচ্ছা 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 ঠিক আছে। Perhaps there is a problem. Please wait. He is reconnecting again. Please keep patience. Sir, please unmute. Yes.
কোনটা কাটলাম স্যার? Professor Dandopat, are you audible? Okay, sir. Sir, sound is not
आपकी
coming.
आवाज नहीं आ रही सर, आपकी आवाज नहीं आ रही।
Something problem.
Hello. Could you hear?
Sir, you are audible. Please continue, sir.
Okay.
Okay, sir.
I suppose there will be no vibration. Oh, it is coming again. Just a minute. I leave the computer audio. Is it okay?
Now it's
Okay,
okay, sir.
Okay.
Could you hear?
It is clear, sir. Carry on.
Oh, okay.
Yes, sir.
Okay. Actually, for today, my speak, the topic is onset of thermal convection, a gateway to hydrodynamic stability. Now, as far as I understand, that many of the participants, they may not be conversant with fluid mechanics. So I shall try to speak the subject matter of this topic as lucidly as possible. Now, in any way, you may not know studied the fluid mechanics, but you know what is fluid. Fluid is like water, air, alcohol, different types of oils, paints, honey, all sort of things. But all these fluids, they do not possess the same property. Now, few fluids they called is that Newtonian, some are called non-Newtonian. The fluids which obey the simple law, the stress is proportional to the rate of strain. These fluids are called Newtonian. Others are called non-Newtonian. For example, water, air, they are alcohol, they are all Newtonian fluid. Whereas honey, paints, say molten lava, all the things, they are all non-Newtonian fluids. Anyhow, another one thing that fluid, we have seen that in general, two types we observe in nature. One is called laminar and they called turbulent. The laminar flow is a very, what is called, is very layered or smooth flow. For example, if you take a, to paint or anything, then you need a smooth painting or writing from your pen. You need some sort of smooth writing. Sure, these are needed for the laminar flow, but for the turbulent flow, it is completely haphazard and it cannot give you the same result each and every time. Now, one thing that both laminar and turbulent, we need, they are some sort of, we need them in our different types of work. For our example, I can tell you that if you want to drink a cup of tea while you are standing on a bus office and you order for the tea seller give you a cup of tea and you want to drink. At that time, you found that your boss is coming. So what will you do? Will you throw the tea or you will drink the tea and get up on the bus? In general, everybody will do, they will pour the tea on the dish and they will give some sort of food on the tea to create the turbulence on the surface of the tea level so that the tea will be cooled down quickly and you can drink. That means a turbulence, it helps to better heat transport. Sure, it will cool the system very nicely. Another one thing that in between laminar to turbulent, there is a process that is called transition process. That from laminar to turbulent, it won't give directly jump. There is through a process it called the transition zone. We need sometimes that the effect of this transition zone in our study also. For example, suppose, it's a crude example, of course. Suppose you want to make some sort of photographic film. You can remember, today we are using our electronic film, but previously, while we had the camera, those cameras required some sort of different types of film. And we used to put some film at the inside the camera, and while we put the shutter, then pictures are coming. So what is happening? How to prepare the film? They take a what is called your sheet of celluloid tape, and they put the celluloid tape inside the nitrate solution, silver nitrate solution, and then they pull it slowly. Sure, if you pull the slowly, then liquid which will drag with the silver celluloid tape, it will fall under the action of gravity very smoothly and slowly. And at a end point, it will try to thin the fluid film very, very small, and it will be very uniform. But if you pull the strip very fast, then there will be some sort of wave generation will be formed on the surface of the film. Sure, to production of the film, we need smooth film. And if you slowly move, then your production will increase. If you increase the withdrawal, then you can think of that if you can attain the maximum withdrawal velocity so that your film will remain laminar, then your production will be maximized. So in that case, you have to know that how far the flow is stable, how far it is laminar. Sure, in this way, the stability or transition part is also very much effective to know for us. Now, we are interested to know the hydrodynamic stability. This is a part of hydrodynamic stability. Now, what is stability? Stability is just any sort of form, any liquid surface. It is there. Now, if you put a particular small disturbance, then if the disturbance dies down, then we shall say the flow is stable. Now, if you give the different types of small interactional disturbances, and particular one type of disturbance, if the system becomes unstable, then we shall call it the system is unstable. Sure, our form is that to impose a disturbance, interaction with small disturbance, and study how long or how far the film remains or the flow remain stable in the initial state. So in this way, we have to study. Now it's a classical example of hydrodynamic stability, what we are going to study today. Suppose we have a beaker or anything, you want to put some water and you want to boil it. Then what will happen? Have you marked it or not? I don't know. But if you mark, then as soon as you ignite your gas oven, then the fluid will not start convection immediately. It will take some time. It will heat up. That means at the level, at the base level or the base, the fluid will be heated enough, and then it will try to expand. You know, everything, when we apply heat, it expands. So fluid will expand. As a result, its density will decrease and its volume will increase. So it will move further to give the upper denser fluid to come down. So in this way, it will move, it will release the fluid, heat, and then again come down. In this way, the ignition starts. Now, here we shall study it in this form. The mathematical formulation of the problem will be, as you can observe in the slides, that this is the equation of continuity, this is the Navier-Stokes equation, and this is the heat equation. And I'm sorry, those who are not conversant with the fluid mechanics, they can take it granted that these type of equations, but as we all are mathematics students, so everybody of us can handle the mathematics and the partial differential equations. Sure. Here, the things are like this, that this is the grad, it defines it del x, del y, del z. This is a divergence. V is the vector, so it will have three components, u, v, w. Now, this is density, rho. This T is time.
Sir, please share your screen, sir.
I should share the screen? Okay, just a minute, just a minute.
Yes, sir.
What is happening? I don't know. Oh. Just a minute.
Okay, sir. Okay.
Do we need again here?
No, sir. PPT is not visible, sir.
Is it coming?
Yes, it coming, sir.
Okay. Okay. Thank
All
you.
is okay, sir. Carry on.
Okay. Sure. As I told, that this is the equation of continuity, and this is the momentum equation that is called Navier-Stokes equation, and this is the heat conduction. This is divergence of V. V is the vector, so it will have three components, U, V, W, and then this is rho. This is time T. This P is pressure. This is rho nu. Nu is the kinematic viscosity. Then G is the gravity, and lambda, it will have the component 0, 0, 1. That means it acts in the vertical direction. And negative sign, it is because the gravity acts against the z axis. Sure, here kappa is the thermal diffusivity. Now, we will have some basic state. That means at the initial state, we put some liquid and put them on the beaker and heat it up. So at the initial state, there is no motion at all. Therefore, V is 0. And we applied some temperature T, that is a function of Z, and we are saying that T bar. And you can see in the equation of momentum that you see, if V is 0, then the left hand side is 0, this part is 0, only P will balance with gravity term or buoyancy term. Sure. Sure. T del P del Z equal to rho G, where rho is changing. As I told you, that density will increase, or density. This is the part. Alpha is the volume expansion of the liquid, and this is the temperature difference. This is the original temperature at the room temperature, and this is the temperature which we have input due to heating. Now, sure, the equation will come for the basic equation. This is T bar del T square, T bar del Z square equal to 0. So the solution T bar, that means basic solution will be this, where beta is the adverse temperature gradient, that is dt dz. Now the negative sign is due to the form that temperature is decreasing is if we if we move towards the z direction. So it will be negative. That's what, but beta itself is positive. And then this rho will be again this, and accordingly pressure will be, if we substitute, then pressure will be this. Now we shall, under the, with this form, we will have, as we know the basic equation, now we'll give some sort of infractional perturbations. Now, V, the basic velocity was 0, so only perturbation will epsilon ui. Ui means I will have three components, UVW or U1, U2, U3. Temperature, T bar basic plus the perturbation, pressure basic plus the perturbation. Now, here we have used the Boussinesq approximation. What is Boussinesq approximation? It says that all the thermodynamic variables, that means diffusivity, thermal diffusion, diffusivity, then your, what is called your viscosity, all the things, they all also change with the temperature, but the variation will be very small. Alpha will also change, but its variation will be very small. But at this stage, just you see here, all the things, everything, they small are very, very small. But see that variation of density, it is small, alpha is small, no doubt, variation density. But since it's multiplied with G, so it will be maximum. So we cannot neglect the term, that buoyancy term, since it is multiplied with G, it will have higher order. Now, under this is your, what is called, equation of continuity. This is our Potter equation. These are the Potter equations. So I have substituted the Potter part, P bar plus this. So you can see T bar plus epsilon theta. Now, from this Potter equation, if you substitute, if we first we neglect the infinitesimally small disturbances, that means epsilon order square terms will neglect. This term will neglect. Now, here also, just you see this and this term. So we'll neglect this part also. So ultimately, what we'll get? Only this part, epsilon terms of this part. Then here, this part. Because before to get this, we'll subtract the term which are without epsilon. So this part will drop this part also, will drop this part also. This part will have there, because epsilon ui and u is a function of what is called z. It is a function of z. So del t, del z term will be there. But del ui, del theta will be neglected as epsilon square term. So ultimately, the two equations will get these two terms. Now, if we can write them in this form, we can write it in this form, that if we want to, now things are like this. These are the you see equation 15, and 15 is a vector type of equation. It will have three components, that del u del t, del b del t, del w del t, like this. Del p del x, del p del y, del p del z. Similarly, u, v, w, and this part will be with the z component. So if we eliminate the u, v, and p from these equations, then ultimately we'll obtain an equation in terms of w and theta. W is the component, vertical component of velocity. And this is the water temperature equation, where beta is dt dz. Beta is minus dt dz. Now, we need to solve this equation. We need some sort of boundary conditions. Now, what are the boundary conditions? At the level z equal to 0 and d, if we think that, if we assume that thickness of the film is d, So z equal to 0 to d, we'll have that we may have the boundaries are either both the boundaries are rigid, both the boundaries, one is rigid, one is free, and both are free boundary. Now, you may think of that, what does it mean? Both the boundaries are free. You see, it is like this, that if you put some oil over water and try to heat the water from below, then the interface between oil and water can be treated as a free, because since there is no rigid surface. So it is like this. Or you may think of like this, that you are heating some liquid, and above that liquid, air is there, air column is there. So in between, at the interface, there is nothing, nothing is there. So that is the free boundary. Top is free, bottom is free. So both the boundaries are free. It can think of like this. Now on the boundary surface, when it may be rigid, it may be free, both theta will be 0 and W will be 0. What does it mean? Temperature will not change. Your temperature in between these two, they will remain same. The in between the temperature, they will remain same. You are giving the input over here, and this is your top boundary. So, but above the temperature is room temperature. So temperature will remain. Therefore, perturbation will be 0 on both these boundaries or both the surface of the liquid. And similarly, W, it will neither leak from the container or neither it will jump up. So that therefore W will be 0 and Z equal to 0 and D. Now we'll have, so if the boundaries are free surface, if the boundary is free surface, then we'll have the shear stress will vanish, or there will be no shear stress at the surface. Sure. What does it mean? If the boundary conditions are, yes. Hello? Could you listen? Could you hear me?
Yes, sir. Yes, sir.
Okay.
Carry on, sir.
Okay. So boundary conditions for the free, that shear stress must vanish. So shear stress of the fluid is pi xz and pi yz. Therefore, this should be equal to 0. These two will be equal to 0. Now W is 0. W is 0. Therefore we must have del U del Z equal to 0 and del V del Z equal to 0. So on the free surface, both the surface will be 0. Now, if you differentiate the equation of continuity with respect to Z once, then you will have this form of equation. Now you see, del U del Z will be 0, del V del Z equal to 0. So we'll have the equation that del square W del Z square equal to 0 is another boundary condition. So this is the boundary condition for the free surface. Now, we'll use the normal mode analysis. What is normal mode analysis? It is, we have, as I told you, we have given or input the very infinitely small disturbances on the system. Now, the disturbance, we have to study all form of propagation of the disturbance. And the aim of the stability is, if the disturbance grow with time, then we shall say the system is unstable. If it is decay, then system is stable. Now, to give the all sort of form, we have to use the Fourier mode analysis. So this is nothing but, and here F denotes all sort of variables. That means you can think of W, theta, as well as you can think of also U, V, P, everything. And their basic function will be Z, and then exponential function will be. This is that it forms with the form of a wave. It will form in the form of a wave, and pi itself is the phase velocity. Is the phase velocity in which it will move. And the both kx and ky has the relation, because both are in the wave number in the direction, kx is wave number in the direction of x, and ky is the wave number in the direction of y. So k will be this relation. So K is the wave number and phi is the complex wave speed, or it's a complex number. It can be think of that pi equal to omega pi equal to omega plus omega I. Now, here one thing I'd like to say that this is the omega. So omega will have two parts. One is real, one is imaginary. Now, if the real part omega r is positive, then what will happen? With time, it will increase. It will be exponential in the term e to the power, e to the power. So it will increase with time. That means the disturbance will increase. That means the disturbance, the F, will increase with time. That means it will lead to the system to unstable state. If the WR is zero, then WI is there. Then WI, what will give? It will give an oscillation because ultimately e to the power I omega I t. So omega I t, that means e to the power I theta. That means in terms of cos and sin theta. So its amplitude will be 1. It's an oscillatory type. It will be produced. Now, it may happen both omega r and omega I may be 0. Maybe 0. In that case, the form will be a stationary one. The system will produce a stationary one. Now, things are like this, that in general, we have seen that the problem which we are encountering now, there is no basic flow. So, generally, the marginal set will be stationary. It will give a stationary type of disturbance. And if the marginal flow is there is a what is called a motion, then it will never give any stationary flow. It may give some sort of oscillation or something like that. Sure. Ultimately, eliminating and using the Fourier mode will get those two equations in this form, and the boundary conditions are this. Then we use what is called in dimensionless form these two equations and boundary conditions. If we express them in dimensionless form, then we'll get equation number 29 and 30, and what d I have written d equal to ddz. It gives a very disturbing ddz, and pr is the Prandtl number of the fluid, and we have used the dimensionless variables as L is the dimension of length, it is denoted with d. T is the time, it is denoted by d square by nu. And the wave number A, it was kd, and sigma is the frequency, it is p d square nu. Now this, as per the boundary condition, will be this ultimately. Sure, after eliminating theta also, we can have the equation 33. That means everything in terms of W. Now we'll use we shall solve this equation. We shall solve this equation where RA is called the Rayleigh number. It is called Rayleigh number, and in general, as I told you, in this particular problem, it has been observed that sigma is 0. It can also be possible to solve mathematically or show mathematically sigma is 0, but it will take some time. But since the time is limited, I'm just skipping this part. Then ultimately we have the equation putting sigma equal to 0. Putting sigma equal to 0, we'll have these two equations, and after elimination, we'll get W equal to 0, this one. And these are the boundary conditions. Okay. Now you see, if we think that we will have, just you can see, we'll have theta equal to 0, w equal to 0, dw. So w equal to 0 gives two equations, z equal to 0, z equal to 1. D squared w equal to 0, z equal to 0, z equal to 1. And that two. So you are getting four equations, four boundary conditions. And theta equal to 0, we have not used at all till now. Now, here, if we come to this equation, to this form, that w equal to 0, w equal to 0, sigma is 0, then d square minus a square, theta will be 0. Or if we put theta equal to 0 in this 29, then this part will be 0. Since we have already used sigma equal to 0, so d square minus a square whole square, w will be equal to 0. This will give you that d square minus a square, w equal to 0. So you say this is a sixth order equation. This 35 is a sixth order equation. We are having four equations from here. Omega, the w equal to 0. This will be, and here w equal to 0. So a square will not be there. So here, sorry, here it will be whole square. It's a mistake. Please do. There is a mistake. Here it's a mistake. It should be d square minus a square whole square. Just you see. If you put theta equal to 0, then d square minus a square whole square. This whole square part, I have it's a mistake in writing the form. So what we are getting, w equal to 0, d square w equal to 0, and from here d to the power 4 equal to 0, z equal to 0, 1. Now, if you differentiate the equation repeatedly 2 times, then also you can say that all the even order of derivative for w will be 0. All even order derivative for w equal to 0. Okay. So you can assume a solution of this form, that w equal to a sine n pi z, where a may be the amplitude or any constant. Anyhow, if you substitute this into our guiding equation 35, this equation, then you will obtain this relation. Now, for a given a so you see, we are always interested to the lowest mode. What is the lowest value we can obtain? Okay. So if n equal to 1, it will give the lowest mode, lowest value for r. So putting n equal to 1, we'll get ultimately that r equal to this one. Sorry, it will be 1. Sorry, there is also mistake. Okay. So here it will be cube. Here it will be cube. It is also mistake in writing the what is called your slides. Now we are interested to find the critical value of r. That means what value of a or critical value of a to r will be minimum. That means minimize this function. So for this, what we will do, we know that we have to differentiate with respect to a square and then equal to 0. And if you solve this equation 43, you will get ultimately a square equal to I square by 2. And if you substitute the value of a square in our previous equation, you will get the value of RC, which will be this. Then ultimately you will get this. So this is the value of RC. This is the value of RC at which, or that means minimum RC. RC, you can remember, this is nothing but the temperature gradient, whichever was there. You can think of. So when the temperature gradient in dimensionless form, when its value will be 657.5, the convection will start. Then what will be a wavelength? Wavelength will be this one. So lambda will give you the wavelength of the system. Now, this is the full result when this basic flow or basic system there was no flow, nothing was there. When the basic flow will initiate or onset will start at what value? We got our 6 value. And the what should be the wave or what is the wavelength? In which way it will move? You can see this is like this. And this is all. Thank you. Thank you. Now if you have any question, you can ask. I think I'm well in time. Or I've crossed the time. I don't know.
Sir, I have a question.
Yes.
Sir, why you assume a sine type of solution, equation 40, why not exponential?
No. Actually, instead of just a minute.
Equation 40.
Yes. I'm coming. Yeah, this was detail. Actually, you see, sine n pi z. If I assume, then each and every form, it will give 0. Okay. Then otherwise, if you put the exponential, then it may not be. You may not get this type of form. Okay. It is like a trigonometric function. If you take the 2 time differentiation, the same thing will repeat.
Any question from audience? Any question from audience?
Acha, there is one question from Manav Biswas in YouTube Live.
Yes.
He wants to know about the difference between Newtonian and non-Newtonian fluid.
Yes, I have already mentioned that those fluids which obey the simple law, the stress is proportional to rate of strain. This simple law, those fluids follow. They are called Newtonian fluid, and those does not follow, they call the non-Newtonian fluids.
Next. Okay, next question. Next question, Samir?
No, sir, I don't think there is any questions in the chat box.
Chat box. Okay. So,
okay, sir.
Vote of thanks. Anando.
Thank you, Professor Dandapat.
Thank you, sir.
Thank you.
Thank you so much, sir. Very nice lecture.
Okay.
Now we're going to our next session. Our respected HOD will give the vote of thanks. Professor Anandamay Mukhopadhyay, are you here? Professor Anandamay Mukhopadhyay, are you here?
The sound is mute. Unmute, please. Anandamay, please unmute. Okay. Carry on.
Okay, sir.
Again mute. Unmute, please. Sound.
Please unmute, sir. First unmute. Unmute your audio, sir.
Okay. Carry on. Mute again and again.
Anandada, you unmute your speaker because you have muted your speaker. You muted your speaker. You are not audible because you muted your speaker. Kindly unmute your speaker. See yes, now it is working.
Now.
Hello?
Now
Okay, carry on.
now you can
Audible?
go on. Yes, it
Audible.
is audible.
Carry on.
Okay.
Yes, sir.
Thank
You
you.
are
Thank you.
audible now.
Thank you. Thank you.
Carry on.
Okay. Okay. Honorable Principal, Dr. Shiva Prasad Dudro, respected professors, B.S. Dondopat and Sotrid Roy, our most valued participants, my colleagues, and my dearest students. It's my privilege to have been asked to propose a vote of thanks on this webinar program organized by the Department of Mathematics, Vivekananda Mahavidyalaya, Bardhaman. I, on behalf of the Department of Mathematics, Vivekananda Mahavidyalaya, and on my own behalf, extend a very hearty vote of thanks to all speakers for gracing your important work and sharing with us your findings and opinions today. A big thank you to Professor B.S. Dondopat, an eminent scientist, a great teacher, and an internationally acclaimed researcher for his efforts towards onset of thermal convection, a gateway to hydrodynamic stability. In hydrodynamic instability phenomena, thermal convection plays an important role, and therefore his lecture would immensely help the young researchers to find their new ideas and innovation. I must mention our deep sense of appreciation for Professor Sotrid Roy, a renowned teacher and researcher in fluid mechanics, for his lucid explanation of a complex topic, linearization techniques for boundary value problems of differential equations. This topic is very much useful for the numerical solutions of various boundary value problems, and we are all inspired by your words. I would like to thank this opportunity to place in record our hearty thanks to the principal sir for the perfect logistic support and guidance he has extended to all of us for this successful webinar program. I also extend my thanks to the coordinator of IQAC, Dr. Animesh Devnath, for his enormous cooperation in the organization of the event. An event like this cannot happen overnight. The wheels start rolling weeks ago. It requires a lot of planning and a bird's eye for details. We are fortunate enough to be backed by a team of very motivational and dedicated colleagues, Dr. Nizamuddin Ali and Mr. Sumit Tamang. Without them, this webinar could not get success. I also thank our senior most and junior most colleagues of our department, Dr. Asim Mukhopadhyay and Mr. Subhajit Roy, for their constant cooperation and inspiration so that this webinar program could be arranged successfully. At last, I would like to thank all the participants, not only from India but from abroad, to show keen interest to participate in the webinar program. Their overwhelming response is an inspiration for us to organize the next webinar in the recent future. I once again thank all for being with us and the participants for their patient hearing. Thank you very much. Nizamuddin Ali.
Thank you, Professor Mukhopadhyay. Now we are arriving at the end of our webinar. Thank you, all of the participants, all of our resource person, and all of our students who is mentioned or not mentioned in every component of the webinar. Thanks to all, and we are going to end the webinar session. Before ending, I request Professor Tamang to put the feedback link again and in our Zoom platform and YouTube channel again. Then we stop and end our last webinar session in last 5 minutes. Professor Tamang, kindly share the feedback link now.
Okay, now will I leave the session? A few minutes more.
Yes, yes, sir.
We can leave.
So, yes, so I have already shared the feedback link in both the YouTube and Zoom platform. And the one who will fill up the feedback form will get another link for the certification in their mail address. So all are requested to put their email ID in correct way. Thank you.
Thank you all. Thank you. Thank you all.
Thank you so much, sir.
Thank you again.
Thank you all.
Thank you
Thank
all the
you.
participants, all the experts.
Thank you.
Now we're
Thank you,
going to
sir.
close the webinar.
Okay.
सर एक मिनट बस हम फीडबैक फॉर्म भर रहे हैं सर आपको जस्ट 1 minute.
Okay, sir. You
No, you
fill
can,
up the
sir.
feedback form.
Yes, sir.
Fill up the feedback form after the session also.
नहीं
There
भर
is a
दिया सर
separate
हमने
link
भर दिया
for
सर भर दिया
Thank you. Somehow the feedback link in the YouTube platform is not clickable. You are requested to copy and paste it in the browser and you can get the feedback form.